Hello and welcome to part 4 of the integration topic, where today we are looking at indefinite integrals. As we've touched on previously, an indefinite integral is different to the definite integrals that we've looked at because there's nothing here or here. There's no x value lower and upper bounds. And so what does that mean for our integral? Well, the initial part is still the same. So for integrals of this nature, we would raise the power by 1, but then we have to compensate by having 1 over that power out the front. And whether you write it like this or whether you put it all together as one fraction, that's up to you. But then there's something else that we need to take into account, and that is a constant. So we usually write that as plus c, so some constant c. And why do we need this here? Well, before we go to some examples, let's just take a little bit of a time to explore this. And we're going to do so by looking at some derivatives. So the first function that I would like you to derive is y equals x squared minus 5x. So before I do it, just pause and have a go at doing this quickly yourself. What is the derivative? So remember, we're deriving, not integrating, so don't get those mixed up. So focusing on the x squared, first of all, we're going to take the power of 2 and bring it out the front. Drop the power by 1, and for the second term, negative 5x, we're just left with negative 5. Okay, great job if you got this. What about this one? Y equals x squared minus 5x plus 2. What's the derivative for this function? Well, hopefully you can see that it's quite a similar function to the one we just did. So the first two terms are going to be identical. We have our 2x and our negative 5. But what's the effect of this plus 2 on the end? Well, remember, when we're deriving, any constant actually goes to 0. So while we could put plus 0 here, we're just going to leave it as 2x minus 5. Finally, what about this function? Y equals x squared minus 5x minus 3. Well, by now, hopefully you're getting the idea. The derivative is once again 2x minus 5, because the only thing that's different is this constant at the end. It still just goes to 0. So graphically speaking, what's happening with these three curves? Well, we'll plot them in Desmos, but before we do, just see if you can tell yourself what's happening. What's the difference, graphically speaking, between these three curves? So here's the first function that we started with, x squared minus 5x. The only difference with the second and third functions is that they have a constant on the end, and all that does is vertically translate our original function. So here is y equals x squared minus 5x plus 2. It's been translated up 2 units, and the third function has been translated down 3 units because of the minus 3. So the only difference is their vertical translation, but in terms of thinking about their gradient, which is what we're doing when we're deriving functions, their gradient is the same at any given x value. So we can see here at 2.5 that each of the parabolas, that's where the turning point is located. So that's where we have a 0 gradient. On to the right, we have positive gradient, and to the left we have negative gradient. And so here's our gradient line, y equals 2x minus 5. So that applies to all three of these curves. And in fact, we could do any parabola of the form x squared minus 5x plus some other constant, and they would all have a derivative function of this y equals 2x minus 5. So all three functions, when we derived them, took us to the same answer of 2x minus 5. So what happens when we want to go the other way, when we want to anti-differentiate or integrate, as we're now calling it? When we start with the derivative being 2x minus 5, which of these functions do we go back to? What do you think? Which one would you go back to? The first one we talked about that had no constant attached to it, or the plus 2, or the minus 3? Which one's correct? Well, they're all correct to some extent, and so that's why we need to generalize it by using a plus c. That is, there's an infinite number of curves that would satisfy. They're all very similar, their only difference is their vertical translation, and that's the effect of the plus c. So let's now do some examples. Our first indefinite integral is 5x to the 9 dx. It's worth noting that any constant can be brought out the front first, right? So it can be helpful to bring the constant out the front of the integral sign, and now we can just focus on finding the integral of x to the power of 9. So we're going to raise the power by 1. Okay, so x to the power of 10 it now becomes, but then we need to put it over that new power, so over 10. Now it's still times by the 5 that's out the front, and at the end we have our generic constant, our constant of integration, c. So it could be any value. All that's left to do now is just tidy up. So the 5 up here and the 10 down here simplify, and we get x to the power of 10 over 2 plus c. And that's how we leave our final answer for indefinite integrals. We do need to include this plus c, as generic as it seems, to show that we actually have a whole family of curves, as I said before, as our final answer. Now, in some examples, and we'll do one for our third example, we can find out this constant of integration, okay, if we are given some further information. Okay, here's our second example, and already it's looking a little bit scarier, but remember we dealt with ones that look like this in the last lesson. The first thing when we see fractions, the first thing to do is to use our negative indices. Right, that generally makes it easier for us. So 1 on x cubed can be expressed as x to the power of negative 3. And likewise, when we see radical signs, or square root sign in this case, we can express it as a fractional with a fractional index. So the square root of x is x to the power of a half. Rewriting it like this then allows us to follow our normal rules. Just give ourselves a bit more room here. Okay, so raising our power by 1, so minus 3 plus 1 takes us up to minus 2, but then putting it over minus 2, there's our first term. Likewise, we're going to raise this by 1, so 1/2 plus 1 is 1.5, but it's usually better to write this as an improper fraction, and then that is over 3 on 2, and then we have our plus c. Let's just tidy up to finish off. So personally, I like to put it back in the form that the question is given. So with this first one, we have a negative. If we want to take this x to the minus 2 and get rid of the minus power, then the x squared needs to go down the bottom, but there's a 2 down there still. So this is 2 lots of x squared, and we're just left with 1 on the top. And for our second term, remember when we have a fraction within a fraction. So the fact that this is over 3 on 2 means that it becomes 2/3. Alright, so 2/3. what's going to happen with the x to the power of 3 on 2? Well, that is the square root, so we still have a radical sign. It's just a square root because there's a 2 on the bottom here, but it's x cubed that is underneath this square root. Okay, so that's just putting it back in the form that we were given, and then we have our plus c. Okay, last example, and this one's a bit of a wordy one. All right, example 3. The rate of airflow into a container is given by r equals 4 plus 3t squared, and that's in cubic millimeters per second. Okay, so r is the rate of airflow, and t is in time. It is time, and it's in seconds, we can see. Now here's the conditions. If there is initially no air, right, now remember initially means when time equals 0. So at the start there's no air. So we're going to use that to help us figure out what the value of C actually is in this specific case. So there's initially no air in the container. We need to find the volume of air in it after 12 seconds. So the first thing we need to do is set up what a rate actually is, and the units can be very helpful here. We have cubic millimeters, so what's that? That is a volume, right? That's a volume. And then we have seconds to the -1, or remember we could think of this, you might like to think of this as cubic millimeters per second, right? Think of it fractionally. But either way, we've got our time there. So our rate is a change in volume with respect to time changing. Okay, so we can express it in this derivative form, and that's equal to 4 plus 3t squared. And ultimately, we are after the volume, right? We're trying to find volume. So we want to come up with an expression where V is the subject. And in order to do that, we need to undo this differentiation here. So we're going to integrate both sides. That'll leave us with V on the left-hand side and the integral of 4 plus 3t squared. And of course, we have integrated both sides with respect to time. The right-hand side we are, because it's dealing with t. So let's go ahead and integrate this now. Once again, we'll give ourselves a little bit more room. So the first term of 4, that's nice and easy. When we integrate, that just becomes 4t. The second term, 3t squared. If you can recognize that this is t cubed, that's awesome. Otherwise, you can raise the power by 1 and put it over that new power, and then you can see that the 3 here cancels with this 3 here. And then we go on to our next line. No, not yet. We've got to add in plus c, right? Don't forget our constant of integration. We can't leave our answer like this. We're asked specifically how much air is in the container after 12 seconds. So this is where we need to use that initial information. So when t equals 0, we were told that there's no air in the container, right? So the volume of air in the container is also 0. So substituting that information in to this equation here, we have volume equals 0, and then we're also substituting t equals 0. And 4 lots of 0 plus 0 cubed, well, that's just 0, isn't it? So for this particular example, it actually works out that the constant we're after is 0. But sometimes it may be something else. Now that we know C is 0, let's just rewrite our formula for volume. So V is equal to 4t plus t cubed. Now we can go on to the last bit of this question, which is to figure out how much air is in the container when T equals 12. So we have 4 lots of T, or 4 lots of 12, plus T cubed, or in this case 12 cubed. When we compute what this is, it's 1,776. Now, units are important here. Okay, so we'll include the units in our final little statement. After 12 seconds, the container will hold 1,776 cubic millimeters of air. And remember, these units, we can get them from the original question. Great job, guys.